the floor is yours.
Wonderful, thank you. Thank you for the introduction and the invitation. So yeah, I'd like to talk about some stuff related to motivic analogs of the Hopf invariant 1 problem, but I'm gonna kind of start off by talking about some background on kind of the classic Hopf invariant 1 problem and, well, what is this lambda algebra that's also appearing in the title. So that'll be the first part, and then I'm going to move on to talking about some analogs of these in motivic homotopy theory. And once I get to the new stuff, this is all going to be work that's joint with my collaborators Dominic Culver and J.D. Quigley. So, well, what's the goal here? Maybe one general goal that I have as a stable homotopy theorist who likes computations is, if I have some spectrum X in the sense of stable homotopy theory, what I want to do is maybe compute the homotopy groups of that spectrum. For instance, if I have maybe a finite complex, I want to compute the stable homotopy groups of that complex. And of course, this turns out to be kind of notoriously difficult. So instead of working towards that goal, sometimes you set your eyes on a more modest goal. You go ahead and try and compute the homology groups instead. And throughout this talk, homology is always going to be homology with kind of mod 2 coefficients. Really everything that I do is going to be mod 2. So you start wanting the homotopy groups, maybe you can compute the homology groups instead, and you can always try to relate these two things. There's always a way of relating homotopy groups and homology groups given by the Hurewicz map from the Gaussian spectrum X, from the homotopy groups of X and the homology groups of X. But so you can think of this as giving a way that the homology is approximating the homotopy groups, but it's not that good of an approximation. This map is never an isomorphism unless you started with, say, the zero spectrum. And well, maybe you might object that, of course, it's not an isomorphism because I've taken this convention that I'm only looking at mod 2 homology. But even if you looked at integral homology, you might get something a bit nicer, but it's still really never going to be an isomorphism except in kind of a rational case. But there's an idea that maybe the fact that this isn't an isomorphism is not so much a deficit of homology or mod 2 homology or anything like that, but a deficit of what exactly we're looking at. So if you look at the mod 2 homology of X, well, what is this? This is, of course, it's a graded vector space over the finite field F2, but there's a lot more structure going on. Namely, the homology groups of X are a module over the Steenrod algebra of operations in mod 2 cohomology. And well, depending on your perspective, maybe you prefer if I called the homology groups of X a co-module of the dual Steenrod algebra, but that's more of a mouthful, and it's also a module of the Steenrod algebra. So that's what I'll be calling it. In any case, so we have this Hurewicz map, and the key observation here is that all the elements in the homology of X that are in the image of this Hurewicz map kind of have a trivial action by the Steenrod algebra. The sort of primitive elements with respect to this Steenrod algebra action, and the way you can formalize that is that this Hurewicz map factors through a subset of the homology of X given by the maps from the homology of a point to the homology of X with respect to the Steenrod algebra action. Kind of A module maps where A is the Steenrod algebra from the homology of a point to the homology of X. And so this gives a slightly better Hurewicz map. Basically, you should think of the target as not being the homology of X, but really this set of primitives in the homology of X. And this is better in a precise way, namely it's sometimes an isomorphism now. This modified Hurewicz map is an isomorphism if you plug in, say, mod 2 Eilenberg-MacLane spectrum or a direct sum of these. So now what you do with this, and this is kind of Adam's insight back in the 50s, is that so you want to, if you have your spectrum X, you want to get the homotopy groups of X. But now we're looking at this other functor defined on X, the primitives in the homology of X. This other functor is, of course, not homotopy, but it's agreeing with kind of homotopy if you're looking at some direct sum of copies of these mod 2 Einberg-MacLane spectra. So if you have a general spectrum, what you should do is, well, resolve it by these spectra that are behaving well with respect to this functor. If you have some general spectrum X, you should resolve it roughly in the sense of an injective resolution by copies of these Einberg-MacLane spectra. And when you do this, this leads you to, well, Adam's spectral sequence, or the Adams spectral sequence. And this is a spectral sequence that, well, what's the input? The input is, so you've resolved X by copies of these Einberg-MacLane spectra. If you hit this kind of a resolution with this Hom functor, you're getting derived functors of Hom. And so this spectral sequence, the input is really X'd over the Steenrod algebra for the homology of a point against the homology of X. And it's converging to the homotopy groups of X. And this is a great tool in homotopy theory. It lets you try and compute the homotopy groups of X starting with the homology of X. And just a bit of notation. So I'm mainly going to focus on the case where X is the sphere spectrum, which makes this intro a little bit funny because the Fravitz map isn't very interesting for this sphere, but the Adam spectral sequence is very interesting for this sphere. But just as a matter of shorthand, these X groups, in the slides, they'll be written just sort of a X star and a sub CL kind of for classical, as opposed to what we'll be seeing later with Motivic, but I'll be calling these the cohomology, the Steenrod algebra, because the Steenrod algebra, it's kind of this augmented algebra, and these X groups are the cohomology groups. And I'll abbreviate these stable stems in a similar way. So that's the Adams spectral sequence, but Adams did not introduce his spectral sequence just to have fun defining a spectral sequence. He introduced it really to resolve problems in homotopy theory. And in particular, the big success that he introduced it for was to resolve the Hopf invariant 1 problem. So I want to review this not in kind of the most classic formulation, but in the formulation that's kind of most useful for this talk. So what is to this talk, at least the Hopf invariant? Well, say I have some class in the stable homotopy groups of spheres, maybe some alpha. One thing you can do with alpha is look at the map induced in homology and mod 2 homology by alpha. And if alpha is in, say, positive stem, sort of above pi naught, so maybe pi t minus 1 for t greater than 1, just for degree reasons, alpha has to induce the 0 map in homology. And what that lets you do is it lets you compute the homology of the cofiber of alpha very easily. So in this case, if you look at the cofiber of alpha, it's a certain 2-cell complex with kind of a cell in degree 0 and a cell in degree t. And so the mod 2 homology is going to fit into a short exact sequence where you have a copy of F2 on the bottom cell and a copy of F2 up on the top cell. And well, that tells you the homology of the cofiber of alpha. It just, well, it's a dimension 2 vector space on a class in degree 0 and a class in degree t. But of course, the homology of the cofiber of alpha isn't just an F2 vector space. It has this Steenrod action. And what this short exact sequence is telling you is it's telling that the homology of the cofiber of alpha, it's really an extension of these two sort of trivial modules over the Steenrod algebra. And so it's classified by, well, something in the group that classifies extensions. It's classified by some element in X1. And so the Hopf invariant 1 problem, I can phrase it as asking, well, this gives a way of producing classes in X1, but conversely, what classes in X1 can you actually get this way? And I like to think of this as, kind of a question about realization of modules over the Steenrod algebra. It's really asking what module of the Steenrod algebra, kind of these algebraic objects, are actually coming from geometric objects, are actually coming from as the homology of two cell complexes. Well, so this is something of an algebraic construction, but there's the atom spectral sequence that also has to do with X, and these two things are very closely related. Well, it turns out that if you're thinking about classes on the one line and you want to think, when are they coming from the homology of a two-cell complex? Well, it turns out that one of these classes in X1 comes from the homology of a two-cell complex, if and only if it's a permanent cycle in this atom spectral sequence. And this is a bit of terminology. If E is sort of coming from the homology of a two-cell complex with attaching that alpha, I'll say that E is detecting alpha. So now I can state the Hopf invariant one sort of theorem or collection of theorems. So first of all, of course, if you want to ask what classes in X1 are coming from the homology of two cell complexes, you need to know what is X1. Well, this is kind of the first cohomology group for the Steenrod algebra. So it's really the question about kind of minimal generators for the Steenrod algebra. And so, although he didn't quite phrase it like this, this comes from work of Adam on relations in the Steenrod algebra. It turns out that X1 is not so bad. It's just generated by certain classes HA for all natural numbers A, where HA is some class that's in stem 2 to the A minus 1. And by stem, I mean that, well, if HA is detecting some map, then it's detecting a map in pi 2 to the A minus 1. So we have all these kind of potential elements, all these things that could be coming from the homology of two cell complexes. And some of these we know come from very explicit two cell complexes because, well, we have classical constructions of these. Namely, the first four of these, H0, H1, H2, and H3, detect the classic Hopf vibrations. This is kind of one reason why you might call this the Hopf invariant one problem, or kind of one of the relations there. Relates because there's a Hopf invariant. This H is kind of a Hopf invariant of sorts. So these detect the first four Hopf elements, 2, eta, nu, and sigma. And then what maybe one thinks of as the Hopf invariant one theorem is Adam's theorem that he used the atom spectral sequence for in 1960. He proved that, well, you have those four classic classes and that's all. You don't get anything else. More explicitly, there's a non-trivial D2 differential on HA plus 1. It's hitting H0 HA squared, and that's non-zero for A at least 3. So the fact that we didn't have more Hopf vibrations isn't because the old geometers just couldn't find them. It's because they really didn't exist. Now, Adam's original solution of the original proof here is a little bit involved, kind of involving an analysis of secondary operations in mod 2 cohomology. And well, one reason perhaps that the original proof is a bit difficult is because at the time we didn't know too much about the cohomology of the Steenrod algebra. These are the theorems where Adams is introducing really the atom spectral sequence, and there's no reason to care about the cohomology of the Steenrod algebra without these sorts of theorems. But well, with that work, it's something to care about. And these days, we know quite a bit about the cohomology of the Steenrod algebra. For instance, computers can compute it basically any finite range that you want, and we know various structural results. But one of the earliest kind of big breakthrough computations was work of John Wang. What he did was he completely computed the cohomology of the Steenrod algebra through the 3 line. So kind of H0, H1, H2, and H3, as well as a bit of what happens in X4. And he used this really deep understanding of the cohomology, the Steenrod algebra, to, well, give another proof of the Hopf invariant one problem that's kind of much simpler than the original proof. He gave kind of a really clever inductive argument for these Hopf differentials. The base of his induction, you need to know something about, well, what is the differential on H4? But there's kind of gives an easy little one-liner for this that uses a bit of homotopical input. This turns out to be kind of a formal consequence of the homotopical class, the homotopical fact that you have this class sigma, and sigma squared is 2 torsion just because sigma is in, well, odd degree, and these stable stems are a graded commutative ring. And that forces this differential. So you need a bit of homotopical input, but just a little bit. And after that, the part that I want to emphasize is that all the other differentials are just purely algebraic given this. It just, I mean, it's a really beautiful, clever argument, but it's just a bit of kind of mucking around with Leibniz rule and relations in the cohomology of the Steenrod algebra. So it's good to know as much as you can about the cohomology of the Steenrod algebra. Well, Wang did this computation. How did he do the computation? He used the Lambda algebra. So the Lambda algebra is something constructed in this kind of the short little 6-author paper, a lot of big names. The Lambda algebra, what it is, it's a certain differential graded algebra that kind of lets you compute the cohomology of the Steenrod algebra. So it's a differential graded algebra that's, well, satisfies a few nice properties. So it's very explicit. You have very explicit generators and relations, and you have a nice kind of admissible basis of monomials in terms of these generators. Second, the homology of this DGA is exactly the cohomology of the Steenrod algebra. Those 2 points together are not necessarily very interesting because, well, the Kovar complex also satisfies these 2 things, but maybe the point is that the Lambda algebra is not the Kovar complex. It's a whole lot smaller than that. It's quite a bit smaller than that. Now, the Lambda algebra is still fairly complicated. I think I'm not going to give formulas right now, but we'll see some formulas later on. It's not obvious, and it wasn't obvious when they introduced this Lambda algebra that it would be useful for any kind of computations, but, well, it turns out that it is, and is really Wang's work that first showed that it can be very useful for these sorts of computations. Now, the original construction of the Lambda algebra is very interesting, but it's maybe a little bit obscure by compared to more modern, more commonly used modern methods. But there's another approach to understanding or constructing the Lambda algebra that sheds a lot of light on the algebraic properties that comes a bit later from work of Stuart Priddy in 1970. So what Priddy did was he introduced this notion of a Koszul algebra and studied kind of the Koszul complexes of Koszul algebras. And he showed that the Lambda algebra comes up kind of purely algebraically as the Koszul complex for the Steenrod algebra. The original construction of the Lambda algebra is not a purely algebraic construction. It's kind of a homotopical construction. It's very interesting that it comes from something homotopical, but ultimately the algebraic construction is in many ways a bit easier to get your hands on. And well, this Priddy's construction is actually, it's fairly simple. It takes a bit of work to get the details sorted out, but it's a very nice idea. I want to give the brief outline of kind of how the Lambda algebra is coming up from this perspective of Koszul algebras. The main input here is that the Steenrod algebra is actually, it's a filtered algebra. So the Steenrod algebra is generated by these Steenrod squares. And so you can define a filtration by saying that, well, the nth filtered piece is what you get by looking at products of at most n squares. So we have a nice filtered algebra, and anytime that you have a filtered algebra, well, if you want to compute its cohomology, maybe instead of looking at its cohomology, take the associated gradient of your algebra and look at the cohomology of that first. Hopefully by taking the associated gradient, you sort of killed enough stuff that you can get something that's easier to compute. And you can relate these by spectral sequences. There's always, it says a general construction, there's a spectral sequence going from the cohomology of the associated gradient of a filtered algebra to the cohomology of the algebra itself. Now, what's special in this case is that the spectral sequence for the Steenrod algebra with this filtration is actually collapsing. It's collapsing in the sense that, well, you have the spectral sequence starting with the cohomology of the associated gradient of A. So that's, if you'd like, the E1 page. And so it carries kind of the D1 differential, making the cohomology of the associated gradient of A into a differential graded algebra. And the cohomology of the Steenrod algebra is the homology of this differential graded algebra. And well, the situation is actually a bit better. It not only collapses, it kind of collapses in a particular way. And if you look at the particular way that it collapses, you can kind of turn that into, it's really equivalent to the Koszul condition. So the relation to Koszul algebra is coming from the fact that this thing collapses. And well, another nice thing about the little Koszul story is that you can describe very explicitly the cohomology of the associated gradient of A, as well as this D1 differential. And once you compute that, you then find that it turns out to be the Lambda algebra. So the Lambda algebra has this nice kind of simple algebraic construction. And while the Lambda algebra has seen various applications, of course, there was Wang's solution to the other solution to the Hopf invariant 1 problem, but there's been a lot more since then that I'm not going to give any kind of comprehensive overview. I just had room on this slide for only 3 bullet points, so I chose 3 that I'm fond of. One is that, so the structure of lambda, at some point, I guess Ed Curtis noticed that lambda is built in kind of a almost inductive or recursive kind of manner. And this gives rise to a strategy for trying to compute the homology of lambda. This strategy was kind of pushed in hand computations by, I guess, Curtis, and later much further by Whitehead. But we made a lot more progress on that front when Tangora kind of implemented and refined some computer programs for computing the homology of the Lambda algebra. And this gave maybe not quite the earliest, but some of the earliest computer computations of the cohomology of the Steenrod algebra in sort of a wide range of degrees. Then, well, much later, a couple fairly recent applications of the Lambda algebra have been, so Wang uses Lambda algebra to compute kind of x through the 3 line. It turns out you can keep going fairly recently. So Lin and then more work by Chen, they've used the Lambda algebra to completely compute the cohomology of the Steenrod algebra through the 5 line. It turns out that things get a little bit hairy after the 3 line and some other impressive computations, but you're able to do it. And then much more recently, Wang Xu, they use the Lambda algebra to study basically the algebraic Atiyah-Hezurek spectral sequence for real projective space. It turns out that lambda, these kind of classic ways of computing the homology of lambda generalize to give information about things like Atiyah-Hezurek attaching maps and so forth. And so they implement this and they get a lot of data about RP infinity. And this is one of the big inputs to their big theorem that, well, the 61 stem is 0, which, well, if you put it like that, it's a bit obscure, but the big geometric upshot of that was that there's a unique smooth structure on the 61 sphere.
And that Wang is Gaussian, right? So
yes, sorry, yeah, there's multiple Wangs.
Right.
this one is Iskos and Wang. Yes, which is why I guess I used the other Wang's full name, but not here. Yes. So, okay, so this is kind of end of the review part of the talk, which actually I guess makes a good time if there are any other questions. Great. So now I went to.
Oh, actually, sorry, I did have a question. Just out of curiosity, when you say that Tangora introduced some computer algorithms to compute this homology of the Lambda algebra, is the more recent progress mostly just better computational power, or have we refined the algorithms as well? Do you know a little bit?
So for the furthest computations of the cohomology, the Steenrod algebra, they're not going to be using the Lambda algebra. They're going to be using kind of minimal resolutions. Well, the Lambda algebra gives you, and this is something that won't really be coming up in this talk, it does give you some other information, like information about the unstable atom spectral sequence, sort of just comes out of the algorithms for computing. But our recent sort of the way that we know a lot of the cohomology of the Steenrod algebra now is not quite through the Lambda algebra, but through minimal resolution.
Great, thank you.
Yes. So now I want to kind of move on to more new stuff, the stuff that we've been doing. So far this talk, I guess, mostly focused on the sphere spectrum, kind of this really important central object in the category of spectra. But so the category of spectra, it's this nice place for doing stable homotopy theory. And these days you care not just about kind of the stable homotopy theory of spectra, but also about, excuse me, maybe other stable homotopy theories. And in particular, I'm gonna hone in on Motivic stable homotopy theory. Now, if you know Motivic stable homotopy theory, that's great. And if you don't, that's also great, because you don't really need to know much of Motivic stable homotopy theory for what I'm going to be talking about. I just need really some general properties of this Motivic context. So, well, what is this Motivic stable homotopy theory? Well, this is something introduced by Blavatsky and then pushed forward by many other people. I guess he introduced it in the 90s. What this is, okay, I guess a bit more generally than this, but let's just say that for every field F, there's some category of F motivic spectra, which is built in this perhaps slightly complicated way from the geometry of smooth schemes over spec F. But well, it satisfies a few properties that I want to focus on. So first of all, F motivic spectra kind of behave like spectra. If you're able to work with spectra kind of formally, or if you're able to work with triangulated categories, for instance, then you can work with F motivic spectra, broadly speaking. There is an important difference from spectra, which is that we consider the category of motivic spectra as kind of having more sphere objects. Instead of just having kind of Sn for every integer n, really we have, yes.
Hi, sorry to interrupt. So is that for any characteristic of F?
Yes. To my knowledge, yes. You have this for any field F, yes. I'm going to be very soon on to kind of mod 2 stuff, and then I need to restrict the characteristic, but it is a fairly formal construction.
Okay, thank you.
Yes, so we have kind of bigraded spheres, and thus all our homotopy groups are going to be bigraded. And here I make the characteristic assumption. So if the characteristic of F is not 2, then there's a kind of good theory of mod 2 motivic cohomology. And I guess that you have a theory, even if the characteristic is 2, but things get a little bit hairier. And by good, I guess I mean that you have there's a motivic Steenrod algebra that is understood. as well as, in particular, a motivic atom spectral sequence, going from essentially the cohomology of the F-motivic Steenrod algebra, so in the slides will just be written XF, and converging to F-motivic stable stems, or really some kind of completion of the homotopy groups of the F-motivic sphere spectrum. So, well, now we have more stable categories, and we have an atom spectral sequence. So, at least from one perspective, you're kind of ready to go ahead and start computing. Maybe a little bit of background on some things about this motivic context and some computations. So there's been quite a bit of work that's gone into computations in motivic homotopy theory, and I'm not giving anything like a comprehensive overview, but just touching on a few points. First, some cases about particular fields. So if you're looking at the case of kind of the complex numbers, or the C-motivic case, more generally other algebraically closed fields, this case turns out to be most closely related to classical homotopy theory. By a bit of magic, kind of C-motivic homotopy theory turns out to be closely related to more classical homotopical objects like the Adams-Novikov spectral sequence. And well, in particular, it's something that you can care about, whether you're coming from the perspective of caring about motivic stuff, or if you just care about classical stuff. So C-motivic is very useful. And in particular, Isaacson, Wang, Xu, they've used C-motivic methods to compute, well, say C-motivic stems through around the 90 stem. And this was also that you can recover the classical stable stems through the same region. And this is the kind of one of the best methods that we have for understanding even just the classic stable stems, is through this C-motivic homotopy theory. Has some additional kind of computational grip on what's going on. Another nice characteristic zero field is, well, the real numbers. So complex numbers is closely related to classical homotopy theory, and the real numbers are kind of related to the complex numbers, except, well, if you go from one to the other, you kind of have a Galois group fitting in. You have an action by kind of C2 when you go from R to C, and well, roughly that's telling you that our motivic homotopy theory is going to be closely related to C2 equivariant homotopy theory. And so once again, you can come at this either caring about motivic stuff or caring about more standard geometric stuff. It's giving you a lot of good information about C2 equivariant homotopy theory. And some people, including Duggar Isaacson and Boma Isaacson, have computed our motivic stable stems, done some great computations up through a certain range. And then for something that doesn't really connect so much to classical homotopy theory, namely finite fields, it turns out different stuff happens over there. Wilson and Osphere have some computations of, say, FQ motivic stable stems for Q and odd prime power up through around the 20 stem in weight 0. And there's been work on the atom spectral sequence for other fields, but maybe not so much for the sphere spectrum itself, as far as I know. So yeah, I guess I didn't mention, but all of these computations, oh, I guess it's written there. All these computations proceeded via studying the motivic atom spectral sequence. And so I want to make some comments about this motivic atom spectral sequence, namely the input, these X groups. So roughly speaking, the C-motivic case, these X groups are, it's kind of the easy case. These C-motivic X groups are very closely related to classical X groups, in particular the algorithms that people have, say, for computer computation for classical X groups, and these would be algorithms via minimal resolution and so forth. Those could be adapted fairly readily to compute C-motivic X, and so we have a lot of grip over that. On the other hand, well, the R motivic case is kind of the opposite. It's in some sense the hardest case. So there is something precise to say that I won't say, but roughly speaking, if you understand R motivic X and you understand the F motivic cohomology of a point, then you can recover F motivic X fairly readily. And so I'm gonna focus on the R motivic case, but related to the C motivic case. What's happening in this R motivic case? What is the R motivic kind of cohomology of a point? Well, classically, the homology of a point is just F2, but here you get a bit more. It's a polynomial ring on two variables, tau and rho. On the other hand, if you look at the C motivic case, you're getting kind of the same thing, but without rho, or more precisely, the C motivic case is like the R motivic case, but mod rho. And one thing that gives you is you can relate kind of C motivic homotopy theory to R motivic homotopy theory, basically via studying what happens when you go from when rho is killed to when rho is not killed. And computationally, that takes the form of a Rho-Bochstein spectral sequence, where for X, this was originally introduced, studied by Mike Hill. And so there's a way, kind of a Rho-Bochstein spectral sequence from going, for instance, from C motivic X to R motivic X. And this has been the main way that we have for computing R motivic X. Now I want to move on to, well, the actual new stuff. So everything from this point is going to be describing kind of some joint work with Dominic Culver and J.D. Quigley. So some observations, though, about some work that's been done in the motivic case. So these computations of motivic stems have mostly been kind of stem by stem. This is, of course, very hard stem by stem computations in some finite, possibly large range, as well as for particular fields F. And well, when you think of sort of infinite families of computations, you think maybe the Hopf invariant one differentials, and there is at the time no known motivic analog of the classic Hopf invariant one theorem. So while we look at this, and well, the classic Hopf invariant one theorem, Wang had his proof of the Hopf invariant one theorem, that is a little bit of fairly formal homotopy theory, and then just pure algebra. And it seemed like that approach to Hopf invariant one theorem could generalize to really any kind of setting where you have a good grip on cohomology of the relevant Steenrod algebra. And so this led us to ask, well, can we do this motivically? In particular, can we construct a motivic lambda algebra and use this to compute motivic X, and then go on to compute motivic Hopf invariant one differentials?
Sorry, William?
Yes.
Just in terms of syntax, that gadget should be, is it a bigraded differential algebra? No, the motivic lambda algebra we're looking for. Is it just now bigraded, or is there something even fancier in the background?
So the motivic lambda algebra, it's trying to compute X-def. It's going to be something that's kind of like the Kobar complex for this bigraded algebra. So it'll be like a chain complex of things that have a bigraded internal degree. And so
okay, so overall it's trigraded because there's the internal bigrading plus the homological degree in the resolution. Got it. Yep. Thank you.
Yes. So the lambda algebra is like a quotient of the Kobar complex, and well, it'll be the same case motivically. So we went to motivic lambda algebra, and at first it seemed there's kind of some roadblocks to, well, there's definite roadblocks to applying the first construction, but you can sort of immediately move on to looking at Pretty's construction. And there are some roadblocks to applying Pretty's work on causal algebras, because the motivic Steenrod algebra is fairly complicated. It's a bit different from the classic Steenrod algebra. Particularly, it's an algebra over this polynomial ring F2 tau rho. But when I say it's an algebra over this, well, I guess one thing is that it's not an augmented algebra. So from the start, you have to be careful what you mean when you talk about the cohomology of it. And another complication is that when I say that it's an algebra over this guy, I mean really it just means that there's a map of, say, algebras from F2 tau rho to the Motivic Steenrod algebra. But this is actually not sort of, the coefficients are not contained in the center of the Motivic of Steenrod algebra. This class tau is sort of not commuting with all the squares. So on the face of it, there's some roadblocks, but it turns out if you take the right sort of definitions, then Pretty's work really does apply in this kind of context. And by the right definitions, I mean, roughly, I gave kind of a very brief overview of the construction of the Lambda algebra, kind of looking at the filtration on the Steenrod algebra, and that approach modifies fairly easily to the motivic context and to anything that's, well, really any context where you have filtrations. You can try and talk about Cazul stuff. So you can get past this roadblock, and then this leads you, well, you can show that our motivic Steenrod algebra is, in a certain sense, Cazul, and compute the relevant Lambda algebras. So this leads to first theorem, which is that if I have any field F of characteristic not equal to 2, then there is an F motivic Lambda algebra. And I'll give formulas on the next slide, don't worry. So this F motivic Lambda algebra, it is very explicit. You have generators relations and a nice basis of monomials. So it's explicit, it's relevant in the sense that yes, there's a question in the chat of, is the point that the dual motivic Steenrod algebra is a Hopf algebroid, not a Hopf algebra? Yes, that is in some sense the point. And you can also say what you get sort of in the non-dual thing as well. You can describe the structure, sort of the dual of the Hopf algebroid structure on that as well, but yes. So the second way is that this motivic Lambda algebra is relevant in the sense that, well, its homology is F motivic X, and it's a very explicit isomorphism, so it's compatible with all sorts of structure like products and Massey products. One other important point, which maybe I won't have a chance to say too much about, which is that X carries various algebraic Steenrod operations, and in particular, there's an operation square 0, and this lifts to the motivic Lambda algebra, sort of to a map of DGAs. And third, this motivic Lambda algebra deserves to be called the motivic Lambda algebra. It's kind of generalizing the Lambda algebra in the sense that, well, it's a construction that's compatible with base chains. And if you look at the complex motivic case, in general, you can go from C-motivic stuff to classic stuff by setting this class tau to 1. And here it does happen that if you look at the C-motivic Lambda algebra and set tau to 1, you just get the classical Lambda algebra. So in some sense, the most important sort of algebraically universal case is the motivic case. Everything is at the level of algebra, kind of a base chains of this. So, well, maybe it's instead of hemming and hawing about this Lambda algebra, it's best if I just write down some formulas. So this motivic Lambda algebra, it is in some ways very similar to the classic Lambda algebra. I guess the slide says for those who like formulas, and I consider myself one of those people. So this Lambda algebra, so it's generated over the coefficient ring F2 tau rho by various classes lambda n. And it has a base of admissible monomials that I won't write down, but kind of the admissibility conditions is just like the classic Lambda algebra. Now there's various relations. This is a quadratic algebra. And it turns out that the admissibility condition is that there's going to be a relation if you have two integers, well, natural numbers a and b, there's going to be some relation expanding lambda a, lambda 2a plus b plus 1. And if a is odd or b is even, so 3 of the 4 cases of parity, it's just the classical relation, which I'll point out in a bit. And also the differential on these lambdas is sort of the classical differential. But then there are ways that it differs from the classical case. And here's where things start to get a bit haywire. Just focus on the key points. One is that, so the Motivic lambda algebra, it's generated over this F2 tau rho, but F2 tau rho is not central in the Motivic lambda algebra. This class tau does not commute with the lambda ends. Instead, you have kind of a non-trivial bimodule structure, which is, well, you can write down what you get. It gets a little bit hairy when you have powers of tau. But I just want to say that I'm going to be thinking of the Motivic lambda algebra. Really, it comes up most naturally as a right module. So this class tau, it's not central, and for basically the same reason, it's also not a cycle. In fact, no power of tau is a cycle. There's a non-trivial differential on tau. It's going to be hitting, well, whatever it's hitting, lambda not rho, and all powers of tau are going to be supporting non-trivial differentials. And then maybe the most fun part is, so like I said, if you have numbers a and b, there's going to be some relation for lambda a, lambda 2a plus b plus 1. And if a is even and b is odd, you get a little bit of a mess. You get kind of two, sort of a sum of two big sums. What's going on here? What's the key points? If you look at this first line and ignore the tau, this is the classic relation. And also what you get if a is odd or b is even. You just get this without the taus. However, in this case, you need to add on some powers of tau, as well as this whole second sum, which is all, well, divisible by rho. So if you're looking at, say, the C-motivic case, you would only have this first sum, but in general, you're having this rather big thing. Now, kind of like the classic lambda algebra, when it's first introduced, it's not so clear that you can actually use it for anything until somebody goes ahead and, well, does the computation. It's also maybe not so clear that this is usable, but it turns out to be not so bad to use. So we use the Motivic lambda algebra to basically do a computation in the same range as Wang's computation. We compute the cohomology of the Motivic Steenrod algebra through the 3-line. And, well, it's a bit of a technical computation, but the basic idea is, so work on Motivic X has, the main tool that you have is the Rho-Bockstein spectral sequence. And now we have this explicit DGA, and you can kind of use this explicit and not too big DGA to sort of compute chain level lifts of Rho-Bockstein differentials. And the bookkeeping, you can kind of put things together using kind of ideas inspired by Tangora's work on computed computations with the lambda algebra for the Curtis algorithm type ideas. So you can do the computation, and I'm not going to write down the full result. The answer is a little bit complicated. You get a lot more than classic X, but just to describe a little sample of it. So if you look just at the all-important one line, so the one line of the Motivic X, well, what's going on here? So it turns out that you get a piece that is rho torsion free. Get a copy of, so rho is a permanent cycle. It's sort of surviving to something. And so everything is an F2 rho module. And we have this F2 rho supported on copies of HA for A at least 1. And maybe you recall that X1 classically you have an HA for A at least 0. And this is a general feature of Motivic X, that you're always going to have a kind of rho torsion free copy of basically classic X, but shifted over by 1 in some sense. And it's always going to be, well, sort of canonically a summand. But then you also have all the rho torsion. And the rho torsion is kind of where the fun stuff is, because it's not just the classical stuff. And here it turns out that you have classes that are sort of analogous to HA, but they're going to be rho to the 2 to the A torsion. And well, for each A, you get kind of an infinite family of these. So these are written as though they're tau multiples, but tau is not really a class in here. So it's just kind of the name for the class. So we get this just on this one line, that this whole sum here is kind of a sort of n cross n graded infinite family of classes. But it's not so bad as it looks. If we look at this sum, there's these powers of tau, there's a lot of uniformity here. And this is sort of some tau periodic phenomena in our motivic X. So you can reduce down the work there, as well as turns out that all these HAs are kind of related to just H naught by square 0. So in some sense, if you combine sort of tau periodicity and square 0, this whole second summand is really just generated by H naught, which is a certain rho torsion class. And then when you get up to, well, higher filtration, there's going to be a lot more going on. There's sort of 6 more by infinite families of rho torsion and decomposables and various relations, but running a little bit low on time, maybe I'll skip past that. But I'll mention that this computation gives information about sort of F motivic X for other fields F. Does not quite completely compute XF through filtration 3, but it completely computes it through filtration 2 and much of what happens on filtration 3. So maybe time for one more slide, because to talk a little bit about differentials. Once we computed sort of the cohomology of Motivic Steenrod algebra in a certain range, then we went to do stuff that's not just algebra. We went to actually get analogs of the Hopf invariant 1 theorem. Well, it turns out that for any field F of characteristic not equal to 2, you can describe very uniformly differentials on these motivic Hopf classes. Turns out that there's always going to be D2 of HA plus 1 is, so classically you had H naught HA squared. Here you have H naught plus rho H1 times HA squared. And that's going to be non-zero for A at least 3. And it's a little bit funny because in this project, it sort of followed this direction where we spent a lot of time computing X, and then we turned our energy towards computing differentials. And by the end, we sort of realized that you don't actually need to know all that much about our motivic X to compute these differentials, but well, you need it for other stuff. Maybe I'll briefly sketch the proof and then end there. So Wang had his classical argument for the classic Hopf invariant 1 differentials, and it's a very beautiful argument, and it almost applies verbatim. So it's an inductive argument, and the base case is D2H4, and that just works here. The inductive step also works, except at the very bottom. The implication sort of going from D2H4 to D2H5 breaks down due to the presence of, well, a bit of additional torsion in our motivic X. But it turns out, well, his inductive argument works once you have D2H5, sort of you can go from there to all the higher ones. So you reduce to just needing D2H5, and it turns out that you can reduce this differential actually in some sense very similarly to the D2H4. So this theorem, it's sort of for any field characteristic not 2, and it's nice that it's uniform, but when you want to actually compute something, maybe you want to cut down on possible targets of differentials. So if you want to compute this, what you can first do, it's enough to consider just say the base fields. Just consider say FQ and, well, the rationals, where Q is some odd number. The rationals are a fairly complicated field, and you never really want to compute directly with rational motivic stuff. But it turns out that rational motivic stuff, you can try to compute basically using a Hasse type principle. So you can really reduce to the case of p-adic rationals and the real numbers. There's always a map from q motivic x to the product of r motivic x and qp motivic x for all primes p. And this Hasse map turns out to be injective. It's even a bit better. You can understand what's going on fairly explicitly. And this really follows from, they don't quite state this, but this follows from work of Ormsby and Osbeck on q motivic stuff. And once you reduce to these fields, then you're basically you're good to finish off the proof. So having reduced these fields, I can now kind of ignore the R motivic case. You can handle the R motivic case, well, in its own way. Just ignore that. So it's the other cases that are sort of very distant from classical homotopy theory and need some additional thought. So it turns out there's always kind of a classic constant map from classic stems to motivic stems in weight 0. And what you do is you look at the image of the covariant class theta 4 under this map. This map is compatible with atom spectral sequences, and you find that this covariant class is detected by, well, tau 16 H4 squared, but it's also something that's killed by 2. And well, that tells you that whatever detects 2 times tau 16 H4 squared has to die. And classically, H naught detects 2, but now H naught plus rho H1 detects 2. And so, well, this H naught plus rho H1 times tau 16 H4 squared has to be a boundary. And this differential that we want on D2H5 turns out to be the only way that this can be a boundary. So just like what you would do classically with sigma squared, you just do with sort of an analog of this covariant class. And well, then you have these differentials. I think for sake of time, this is a good place to stop. The next slides are just going to describe basically more differentials. There's more to the story, but this is a good stopping point.
All right, let's unmute ourselves and thank William for a great talk.
Thank you, Williams.
Are there any questions or comments?
I was wondering why there's no, like, you didn't use C or anything. C doesn't appear here. What happens with C?
Yeah, so these classes, say HA, they're sort of defined for any field. And in particular, HA is defined over, say, the rationals. And the C motivic one is going to be just the image under base change from the rational case. So if you get this differential over Q or even just over R, you get it automatically over C. The rho goes to 0 and you get actually what looks like exactly what looks like the classic differential. This D2HA plus 1 is H naught HA squared. In fact, for proving some of these differentials, we do kind of treat the algebraically closed case separately, but Wang's argument really works verbatim for C.
Okay, thanks.
John, go ahead.
Learned in the HKX seminar yesterday that there were maybe is a tau in the C motivic version of that D2 differential. Is that, or is that just a matter of conventions?
Let's see. No, there's no tau.
Okay. I thought it was tau, that the differential in H4 motivically was tau H naught H3 squared.
Is it?
But maybe it depends what the H's mean.
It could, yeah. No, I don't think that there's a tau, at least not with how I would define my H's. I mean, something to say is that these H's are sort of not the classic H's, of course. We've sort of already divided out by tau as much as possible.
That might be the reason, yeah.
Any further questions or comments?
I had a question about the Motivic lambda algebra. You said it's
Yes.
it's kind of like a skew algebra over its coefficient ring, where part of the algebra acts on the.
What is
basis?
skew algebra?
Exactly what you have there. You have part of the ring which doesn't commute.
Okay, then yes.
Yeah. Okay. So my question is, there's a theory for that when you have a Galois ring extension. So F2 tau rho would have to be some sort of finite index extension of something that is central. Is that true in this case?
The biggest thing that's going to be central is just F2 rho. I mean, anything to do with tau is not going to be central at all.
Okay, so it's an F2 rho algebra, and you have this, you can interpret F2 tau rho as a monoid algebra over F2 rho, and it's a skew monoid algebra. Anyway, it's quite an interesting structure that you have here. I don't think I've seen this this exactly in this context, but you know, we might present it a little bit differently in algebra, and then see it differently.
Yeah. I think that sort of in a very simple way, just when I think of it as being an algebra over this, I guess all that I mean is that there's a map.
Yes.
There's a map of algebras. Or if you prefer, it's a monoid in the category of bimodules.
Okay,
So I think this point with the dual algebra is relevant because the dual Hopf algebras are not quite, there are Hopf algebras with sort of two-sided identities, so they're Hopf algebroids. So I think the only structure is that the dual algebra is a Hopf algebroid, which so it's graded commutative and represents a groupoid rather than a group. But there is some discussion in one of those two papers of Wodzki where he constructs Steenrod operations in Motivic homology, where he writes everything in terms of the algebra, and he's very careful about left and right actions and various submodules or subgroups or subrings of multiplicative elements and so on. It is, it's I think it is algebraically describable, but it's, at least to algebraic topologists, it feels like saying that it's the dual of a Hopf algebroid.
Yeah, and once you have enough identities, then you can do your calculations, right?
Yeah. Maybe, yeah, thinking of it as an algebra is useful for, well, for getting the lambda algebra, because you sort of get the relations. These relations are sort of causal dual to the complicated Adem relations. And I think it would probably be possible to get those using kind of the dual Steenrod algebra perspective, kind of like what Pretty does in the odd prime case. But, well, at least when I did the computation, I used the Adem relations, and I didn't care to redo it, try to redo it using the dual Steenrod algebra. So thinking of the Steenrod algebra itself, the Motivic one definitely comes up here.
I mean, if you think of the dual algebra, then there's a cobar construction, and that has a product. And the formula for the product in the cobar construction is usually concatenation, but if you have coefficients, it's a little more complicated. But so either in the appendix for Ravenel's Green Book or in the earlier paper by Haynes Miller, there's some discussion of the product in the, well, I guess it's already in Adams's papers on the cobar construction for the product structure there. So it might be that
the Motivic lambda algebra is a quotient of that. It's just a matter of getting the relations that you're quotienting by.
Yeah. I can imagine the algebra being awful. Maybe I can comment. I had a PhD, or Paul Arne Østvad and I had a PhD student called Thomas Gregersen, who finished 10 years ago. So he actually did some work with the Motivic Steenrod algebra and proved basically the Siegel conjecture. And I mean the Lin and Gunnar-Verdena theorems for C2, for mu2 and mu-p actions. So it basically shows that some sort of inverse limit of standard projective spaces, so the analog of RP infinity minus infinity, is then equivalent to the, in that case, the -1 sphere. But those were all those computations were, so basically it is by saying that the Adam spectrum, that there's a map of Motivic spectra that induces a map of from the atom spectral sequence to an inverse limit of atom spectral sequences, and that map is an isomorphism of E2 terms. So it's entirely non-computational. There's no computation, just like the proofs of Lin and Gunnar-Vardena's theorem, one never actually calculates anything but the E2 term of those spectral sequences. But I'm curious about whether, but so there is sort of an analog of Lin and Gunnar-Vardena's theorem that also leads to these Mahold invariants, if you think in terms of the filtration of RP infinity by Skeleton. And I think that J.D. Quigley has worked on that in the Motivic situation. It would be interesting to see if those differentials that you're seeing, if they somehow, you know, there's this nice paper by Adams of what we don't know about RP infinity, where he sort of quotes various things one knows about the differential pattern in the stable, in the Adams, in the S-space, here's the book spectral sequence for the sphere, and some of those differentials might be the same flavor that the differentials you're starting to see here. So maybe.
Do you mean like as these differentials? Which differentials were you talking about? The Adams differentials or the algebraic differentials?
I'm thinking of no, I'm sorry. No, what I'm thinking about is our algebraic differentials about how the attaching maps are in RP infinity or CP infinity.
I see.
But it's
maybe one thing that maybe
the basic theme, I guess,
is at the very. Oh, go ahead. One thing that you go ahead.
I just meant that the it's kind of Siegel conjecture type result that a certain so that the stable homotopy of some Tom spectrum or CP, RP infinity minus infinity, that is somehow equivalent to just the S0 requires a lot of, that the result is somehow connected, requires a lot of differentials to reach it. And then it's sort of unrealistic to make complete calculations to explain it. But once you have some non-trivial computations like this, it could be interesting to see at least how it fits into a picture.
Yes. So I agree. And I'm not sure if this is what you're getting at, if you were sort of seeing the slides that I didn't get to. This Motivic gadget is very closely related to those sort of real projective space computations. Maybe I'll jump real quick to just mention this thing down here and ignore all the rest. If you look at sort of Motivic X, if you sort of roughly speaking invert tau, you're getting back the sort of classic X for the cohomology of various stunted projective spaces. And it seems like getting the precise formulas is a little bit difficult, but the Motivic Lambda Algebra ought to be some kind of decompletion of the lambda complex that you see when you try and get a lambda complex for the cohomotopy of stunted projective spaces. And then if you invert rho, it's kind of like you're looking at the X for that Laurent polynomial thing. So what's as you say is sort of collapsing down to classic X. So these Motivic computations are very closely related to those sorts of computations, although I'm not sure if this is.
Yeah, but I think what Gregersen proves is that the Motivic the Motivic E2 term is isomorphic. I mean, for mod 2 coefficients is isomorphic to the Motivic X for the Motivic cohomology of a point and the Motivic cohomology of really the suspension of P infinity minus infinity. So I'm not sure what the lower star on your P infinity is.
So this is Rx is trigraded, right?
Oh, I see.
If I inverted rho, then that would be P infinity minus infinity. As it is, it's all the stunted projective spaces at once.
And when I say P infinity minus infinity, I mean the cohomology doesn't quite commute with limits.
Right. Yeah.
So I really mean the co-limit of the cohomologies in the tower rather than the cohomology of the limit. But that's I mean that's sort of the algebraic localization.
Right. And that would correspond here to inverting row. But I guess this is not giving a question of what you say your student did, sort of the motivic X for P infinity minus infinity. This is just saying that our motivic X happens to relate to sort of the classic X for P infinity minus infinity or any P infinity n.
Any more questions for our speaker? If not, then let's unmute ourselves and thank William again. And thank you all for attending. You take care.
Thank you for having us.
Did your student, does he have also